Hi everyone, thank you so much for joining us today for ML Maths guest speaker session. We have with us Jeremy Bernstein. Jeremy is a postdoc in CSAIL at MIT advised by Philip Bacona. His goal is to uncover the computational and statistical laws of nature, natural and artificial intelligence, and thereby design learning systems that are more efficient and more automatic and useful in practice. Thank you so much for your time, Jeremy, and I'm and you do.
Yeah, thank you so much for having me to talk. I'm really excited to be here. My co-author, Tim Large, is also here on the call, so he may be able to help answer the questions as well. In terms of, I was just saying that people should feel free to ask questions during the talk, and I encourage it. Depending on how the timing go, I may later on try to start skipping some questions if we're running out of time, but if there's no questions, it may be like a 45-minute talk or something, but I have an hour and 45 minutes free, so I'm happy to just stay during that time. But yeah, I'll just start. So I have a question, so it's interactive, but the question is why, if you look at this flight plan of flights in the US, why are the planes not flying in straight lines? You don't need to raise your hand.
Right, because you have like spherical coordinates in a way.
Yes. Okay. So yeah, I think yes. So the idea is that when we look at a map, we're looking at a like a 2D projection of the sphere, and this distorts the geometry. So that the Earth is really spherical, and a straight line or a great circle on the planet Earth, if you look at it on a 2D map, it gets distorted. And geometers have a tool for making the connection between the map or the 2D map and the underlying manifold, and they call this the metric. And it's a way of mapping distances on the map to distances on the sphere. And I just want to make a high-level analogy that in deep learning we have kind of the same situation where our description of the system is the neural network architecture and its weights. But the thing that we really care about is the function space, or the decision boundary, or the predictions and so on. And we'd really like to work in the decision space or the function space or something like that. But unfortunately, we're forced to, exactly, function space versus parameter space. We're forced to work in the parameter space. What if we could build a tool, a metric, that helps us map between the two spaces or translate between the two spaces? This is just very high level intuition or some motivation. So what is a metric? Actually, in our situation, things are kind of simpler than differential geometry, perhaps in some respects. But for us, a metric, we just mean a norm. So if we think of a neural network that maps weights and inputs to outputs, we'd really like to just directly control the output. But unfortunately, we only have control over the weights or the parameter space. But then we have an idea. What if, given a norm on the output space, so a measure of distance on the outputs, what if we could construct a measure of distance on the weights, so that if we perturb the weights with a delta W, the size of the delta W in the weight space norm actually predicts the size of the delta output in the output norm? Like, what if we could build such a tool? That would be really helpful, because then we could use it to set how big our weight updates are. Okay. So I came up with this term, like, call it metrized deep learning, and it's the idea of building a kind of machinery that will place norms or you think of a norm as like a measure of how large something is on all the spaces inside a neural network. So if we think about, a kind of cartoon of a neural net, what do I mean by the spaces inside the neural net? Well, one kind of space are the activation spaces, the hidden vectors. And the interesting thing, deep learning people kind of know how to metrize these spaces. And this is why we have tools like layer norm and RMS norm, which impose a scaling or a normalization on those spaces. So we kind of know how to think about those spaces in a sense. Other spaces are the matrix spaces or the individual layers. And actually math people kind of know how to metrize these spaces. And if you talk to a mathematician, they'll tell you about induced operator norms, which given a norm on the input and output space of a matrix, you can actually induce a norm on the matrix space. And this is like something well known in applied math. So we also want to try to do something new. So what's not known? What don't we know? And the idea is that the thing that we actually don't know is how to metrize the full weight space. So let's say that we have norms on our activation spaces and we have norms on our matrix spaces. With a neural network, the weights, you think about gluing all of these matrices together. How can we build a norm on the full weight space? Again, this is just some motivation. And what could this be useful for? Something I think it can be useful for is low precision training. So if you want to save, yeah, by the way, I think the session will be recorded and posted. So just responding to the chat. So let's say you want to save resources like energy, money, and time. A great way to do that is to quantize or discretize your training as low precision as you can. And to me, the fundamental question there is how finely do we need to discretize the input and output and the weight space of a neural net? And to me, that's a question of knowing what length scale is important in each space in the network. So there's a picture here where during training, you can think about any subnetwork, you're changing the inputs to the subnetwork, you're changing its weights, and you're getting a change in outputs. What length scale do you need to be able to represent? And for me, that's intimately connected to the idea of what norm describes distance in that space. Something else it could be useful for is robustness or adversarial robustness. So we've seen that example where we, take an image, we add some small noise to it, and it completely changes the classification. They call this adversarial examples. And again, to me, the fundamental question here is about understanding how a network responds here just to input perturbation, and what are the length scales on the of the input, and how does that relate to the length scales on the output? And for me, this is a question about norms. But those are just some motivations, and actually the application of this stuff that we've most investigated is scaling. So I'm now going to kind of switch gears and start talking about scaling and what it has to do with metrization. Again, just feel free to shout out questions if you have any questions. So even in the natural world, there's this idea that scaling a network or having more neurons leads to more intelligence. And actually, the African elephant is the organism with the most neurons in the natural world. And we've even got this recipe now for really strong artificial intelligence, where we try to get the biggest supercomputer that we can. We scrape as much data as we can from the internet, and then we train the biggest transformer that we can. And this is the recipe that seems to be working really well. But there are a couple of problems with scaling. So here's some cartoons, but one problem is you scale the width of your network, and even though the performance gets better, so I'm plotting training loss against learning rate, and the different curves are illustrations of different widths. You see that even though the performance improves with increasing width, you see that the optimal learning rate kind of drifts. And this just makes it harder to train large-scale neural networks because, naively, you just have to tune the learning rate as you scale the width. Another problem that you see if you do poor depth parameterization is if you scale the depth of the neural net, you see that, even if the optimal learning rate stays fixed, you can see that performance actually gets worse with depth rather than better. So these are two, real problems that you run into if you don't do things carefully.
Sorry, I didn't understand the plot in the second plot, the scale depth. You're saying that if you have bigger depth, your loss is higher? Like, isn't this against the scaling loss?
Exactly. Yeah. So what I'm saying is if you set up your training not in the best possible way, you can see what you see is that you scale depth and you get worse performance. And what we're going to think about in the talk is how to set things up so that you scale depth and you get better performance.
Okay.
But yeah, like my claim is if you don't think of things through really carefully, you'll actually see this in practice. But although the plot is just a cartoon, just to be clear. So by the way, I'm still just motivating. I'm trying to, copy learning rate definitely doesn't always work. Okay, so the idea here is I want to make an analogy with electronics. So in electronics, we have rules for building resistor networks, where if you combine resistors in series, the resistances add, and if you combine resistors in parallel, you add the reciprocals. And these kind of circuit laws or circuit rules have allowed us to build complicated electronic circuits and have good understanding of the behavior of the circuits. But in deep learning, we would like to be able to build complicated neural networks. So the question is, what are the circuit rules for building neural networks? We actually don't have them. So that's another motivation. And what I want to argue in the talk is that this is intimately related to the idea of metrization, or the idea of building norms for my neural network. Okay, so that was all just set up. And now I want to talk a little bit about how we've actually thought about the problem. So we broke up the problem into two pieces. So first we asked, what are good properties for an individual layer in a neural net? And then we ask, now we start to build a neural network by combining layers. How do we keep those good properties even as we start putting things together and assembling pieces? So for the first question, we wrote some papers on this topic, and we think about an individual linear layer, and then think about just changing the weights of the linear layer. So we're just changing the weights of the linear layer. And what we did is we gave these what we call spectral conditions, so conditions on the spectral norm of the weights and the weight updates. And what we say is that you should scale the spectral norms like square root fan out over fan in. And for the weight update, you then also multiply by the learning rate. And the claim is that if you adopt these scalings, then you will get learning rate transfer across width. And there's an argument that somehow the spectral norm is in some sense the natural way to describe the size of a matrix. And that's the argument that we make in these papers. And so just to repeat that, like if you adopt these conditions, if you set the size of your initial weights using the first condition, and you set the size of your weight updates using the second condition, then if you scale your neural network, you can use the same learning rate at any scale. And the point is that they're quite simple conditions, actually. And actually, this got adopted in Hugging Face Nanotron. So like people got some good receptions of this paper, and people are interested in this idea. And what I want to talk more about today is the second question. That is how, if we know how to deal with individual layers, how do we deal with it when we put those layers together and we start to build up a big neural network? And this is
a quick question.
Yeah, please go for it.
On the previous slide, you talked about how we want to control the weights and their gradient updates. How does this relate to stuff in activation space that you mentioned a bit before?
Yes, exactly. So great question. So the spectral norm is the induced operator norm from L2 space to L2 space, or Euclidean norm to Euclidean norm. So if I equip the activations with the input and output with Euclidean norm, then the induced operator norm is the spectral norm. And that means that if I just control the spectral norm, it gives me, hard guarantees on how much the activations can change. Controlling the spectral norm at initialization gives me hard guarantees on how large the activations can be at initialization. And controlling the spectral norm of the weight updates gives me a hard guarantee on how much the activations can change in response to the weight update. Okay, why do the factors of square root fan out over fan in appear? That's because conceptually, we don't apply the Euclidean norm to the input and output space. We instead apply the RMS norm, which is like the Euclidean norm divided by square root dimension. And somehow this is a more natural norm for a neural network than the Euclidean norm. That's why we use, RMS normalization in a transformer, for instance. And the induced operator norm from RMS to RMS is like spectral norm times square root fan in over fan out. So you can view these conditions as like ensuring that the weight updates and the weight initialization have unit RMS to RMS induced operator norm, which gives you hard guarantees on how much the activations can change in the RMS norm. So that's the connection. I haven't really spelt it out, but we'll talk a bit more like in an abstract sense about this kind of thing later in the talk. But yeah, maybe we can talk more. Or if people want to, if you want to discuss more now, we can also just discuss more now.
I have maybe a quick question related to that, because similar work, which is also what you have in the second paper, MUP sort of gives you like this order of one guarantees also on the pre-activations. Is it the same guarantee that you get here with the spectral norm, or is it different? Is it like a tighter bound or something like that?
The thing which I'm writing here, I'm intending to be a summary of that second paper. So I'm not trying to say anything different here. But what it's saying is if the factors in the green boxes, like the square root fan out over fan in, if you move them over to the left-hand side of these equations and sort of absorb them into the definition of the norm, then it's saying that this absorbed norm is order 1 for the weight initialization and order learning rate for the weight updates, and that implies order 1 guarantees on the activations, both in terms of how large they are at initialization and how much they're able to change under a weight update.
Okay, got it. Thank you.
Thanks for the question. Okay, so how do we keep these? Let's just pretend, or let's assume that we actually solve the problem for individual layers and that we can come up with special norms for individual layers. How do we then deal with actual neural networks which combine layers together, and how do things change once we start to build or to grow our network? So this is joint work with the following great collaborators. Tim is on the call. Just as a, I guess, slight advertisement, but they, yeah, like not it's like, yeah, like, anyway, they both got hired by like fancy tech companies, and I'm losing all my collaborators. And okay, but so I want to start this section just by introducing what we did, what we built. We built a package. It's something you can code. So I'm just going to show you like a demo of the API. And then once we've done that, I'll show you some of the results. And then I'll explain all the mechanisms behind what I'm showing you. So currently the package is built in Torch, but you can implement it in with other backends, basically. We import a linear module and a ReLU module. And then I build an MLP by composing modules. So we use the at symbol to do a module composition. And then the point is that I automatically get some helper functions that are automatically constructed with the construction of the top level module. So for instance, I get an initialize, I sample some training data, I do 20 steps of gradient descent. I get my forward function for free, which should be expected. That's pretty standard. I compute my loss. I do the backward. Here, this is just using PyTorch. And then I get my gradient. I normalize it. So this is the key thing of our package, is that by constructing our neural network, we automatically build a normalize function, which I can apply to the gradients. I could alternatively, like compute an atom update and then apply the normalize function to the atom update. But okay, and then I make my weight update with the normalized gradients, and then I zero out the gradients at the end. So the point is that we automatically build a normalized function, and it's built recursively in the same way that the forward function is built recursively. And using it to normalize the gradients is supposed to give me learning rate transfer across essentially all the dimensions of the network, ideally. So this is the kind of like the API for interacting with what we did. And it's really compatible with any, like you can sort of view like a PyTorch as just handling array programming in a sense, and you can really build this in any with any quote unquote backend. And so Jack Gallagher wrote a JAX implementation, and I recently wrote a NumPy implementation where I also implement AutoGrad. And I think if you're curious to learn about the project, that's just a Jupyter notebook or a Colab notebook. And it's probably the best place to start learning, just to get a hands-on experience with what we're doing. And so now for the experimental claim, and then after that, I'll like start explaining how we actually built this package or what it actually does. But we train a GPT for 10,000 steps on open web text data set. And we use Adam as the base optimizer, and then we take the Adam proposed update, and then we either normalize it or not. And the first experiment, I sweep over width and learning rate. And this is just supposed to be standard nano GPT performance without any of our stuff. And you see that you get, as you scale width, you get a lot of learning rate drift. Then we re-implemented our own transformer implementation, which is supposed to be have better properties, essentially. Sorry. And this plot shows testing that, but it doesn't have the normalization. It still doesn't have normalization switched on. And you see our transformer actually has slightly better width transfer than a regular nano GPT, but it's still not perfect. And then this plot is after we switch on the normalization, and now you see that the curves line up nicely, and you can transfer the learning rate across the width. And then the next plot shows depth. And again, like the standard nano-GPT is maybe not so bad, but a little messy. This is like our transformer implementation, which is actually already transferring pretty well. And then when we switch on normalization, it also works pretty well. So it's actually interesting that with the way that we parameterize our network, the way that Adam scales the updates with depth is coincidentally sort of the right way to do it. So we don't see much benefit here from doing the extra normalization, but we have like a pretty good understanding of why that is. And in the paper, we show some other results, like you can get much better training performance on GPT just using SGD as the base optimizer. So there's like kind of a folk result that you cannot train a transformer using SGD. But it turns out that if you normalize SGD using our normalization function, then you get much, much better training performance, closer to that of Adam.
Sorry, one question, like just to get clear, the difference between the column in the middle and the one in the left. So is this only with the weights initialization that you proposed, but without scaling the learning rate?
Right. What are the differences between our GPT and standard nano GPT? One is we have orthogonal initialization. It's pretty much just because we like it better. Like you could do it with Gaussian. It's just a little simpler to get the scalings with orthogonal initialization. But there are a couple other differences. Like we don't use fix-up initialization, like 1/square-root depth multiplier on the last residual, on the last layer of the block. We use 1/depth multipliers, block multipliers. So that's a change. There's a reason it lets us get kind of tight Lipschitz guarantees, basically, but okay. And there's a couple other things, like in the attention, we don't use 1/square-root embedding dimension to divide the QK in the products. We use 1/embedding dimension. Like we just get rid of the square root. We divide by embedding dimension, which is now pretty standard in like Greg Yang tensor programs. They do that. Other people who study the scaling stuff also do that. So there's a few departures from what is standard along those lines. Also, our residual blocks, we take a convex combination between the skip branch and the residual branch rather than just doing 1 plus something. We do like 1 minus a little bit times identity plus. So there's a few, on the whole, they're somewhat minor changes that don't really affect the performance too much. You see, we kind of get the same performance, but they allow us to get Lipschitz bounds on the so that all of these changes are essentially motivated by getting tighter and tighter Lipschitz guarantees. And the interesting thing is we can still train, and we can still train pretty well, at least in our experiments. Big caveat is we still haven't scaled up to like massive scale, so that's still TBD. We still need to do that. But anyway. We did like a quick experiment on scaling context length, and we also got pretty good transfer across context length. So I'm planning now to just switch gear and just start talking about the math. Yeah, so Gilad is saying, by the way, I'm not following all of the chat. I just see some of the notifications pop up. But Gilad, I think I can't read. I just saw the blurb of what you said, but it said it would be exciting to see large-scale performance of spectral normalization. So something I'm going to talk about at the end of the talk. But I've got really interested in Shampoo lately, partly because it won this AlgoPerf like training speed competition. but also because I think that it is actually implicitly just doing spectral normalization. And the fact that people like in big industry labs like Shampoo is the thing that's giving me confidence that the perspective that we have is hopefully going to be the right one, or it's giving me more and more confidence because, you know, like Shampoo is getting good performance in these competitions, and it essentially, I think, is just spectral normalization. So, yeah. Anyway, I'll talk more about that at the end. So now we go to kind of a bit more like math world or theory world, and so I learned from Jack Gallagher about something called Combinator pattern. This is from the Haskell wiki. So Combinator pattern is the idea in program. It's a programming pattern, design pattern, where you build complex structures by combining simple primitives and then defining combinators, which are just rules for combining primitives. And for us, the abstract type is something that we call a module, which is just anything with inputs, weights, and outputs. And given two modules, we have two combinators. So one is composition, which we think of as series combination, and the other is concatenation, which we think of as parallel combination. And concatenation means you take the input, you duplicate it, and then you send it to both modules. And you can sort of convince yourself that if you've got two modules, there aren't, you know, I can't really think of another way of combining them other than, you know, series and parallel. So they're a pretty basic set of like ways of building circuits. Like you either put one and then the other, or you put them next to each other. And I just want to show you that we can build some, you know, some interesting things. Like let's say we want to add two modules. You can concatenate them, and then you define add what we call a utility module that just adds forwards functions and so on, and adds other properties. But you can build module addition. You can build scalar multiplication by doing by composing the module with a special module that just multiplies by a scalar. So these are the utility modules. We can build a residual block. Like here, we want to do A times identity plus B times module. So again, we define an identity. Identity is a special module, a utility module. That looks like this. So we concatenate. We scalar multiply the identity, and we scalar multiply the module. We then concatenate them, and then we pass into the add. So this is just showing that you can build basic neural network functionality from a circuit perspective, doing binary module combination. And as far as we can tell, you can build everything you want to build, you can build in this way, as far as we can tell. We kind of categorize modules into three varieties. So atoms are the ones that you write by hand, like linear, convolution, embedding. That's simple enough that, you know, you can theoretically deal with them, use it by hand very easily. Bonds are the ones which are like atoms, but they don't have weights. So nonlinearities, but also, you know, something like functional attention, by which we just mean the part of attention that doesn't have any weights. And then compounds are the things that you build by kind of gluing together the atoms and the bonds, and you think of compounds as being like full neural networks or subnetworks and just things that are combined together. And the big thing that we want to know, you know, a kind of intuitive way of phrasing it is, what is the sensitivity of a module? So we've got a module with inputs, weights, and outputs, and we think about, you know, either changing the inputs or changing the weights, and that's going to cause a change in outputs. The major goal of our package and our project is to be able to predict how much the output changes in response to both an input change and a weight change. And can we do this for any module? Something interesting is that if you're just doing training, you may wonder, like, why do I care about input perturbations? But the idea is that if you change the weights early in the network, that induces a change in the input to the latter part of the network, to the latter part of the network. So actually, if you want to be able to automatically construct these kind of sensitivity estimates, you need to be able to handle both input perturbations and weight perturbations. And the idea is, let's say that we solve the problem for atoms and bonds. Like, if we can write a module by hand, we know exactly how to do this. How do we do it for compound modules, like for full neural networks? And I'm gonna like hit you with math now, like big math slide, but I'm gonna try to break it up and hopefully make it. Well, let's just see. But feel free to ask questions. So we give a formal definition of a module. It's got input space, weight space, output space, and this was the picture. And we give it 4 attributes, so forward function, a number which we call the sensitivity. This is specifically only measuring the sensitivity with respect to changing the inputs. So think of this as, if I change the inputs this much, then the weight should change this much. We have another number called the mass, which may be not so intuitive at first, but it's supposed to give you more control over the proportion of learning that this module contributes to its kind of parent modules. And while the sensitivity is sort of determined mathematically, there's actually some freedom in the mass, and you can think of it a little bit more like a hyperparameter. Although, okay, I can say more about that. And we have, arguably, the most important thing is the norm. So all modules must have a norm on their weight space in order to be a module. Okay, that's just a definition, and a lot of things satisfy that definition, and a lot of things satisfy the definition and we don't care about them. So the modules that we care about are going to be the ones that we call well-normed modules, where you kind of intuitively, they're well-normed. It means you chose the norm well, you chose the attributes well. And for a module to be well-normed, we need to define a norm on its input space, or we need to choose a norm on its input space. We need to choose a norm on its output space. And then 2 conditions need to hold. So the first condition says that the linearized change in the output of the module induced by changing its weights is measured in the output norm, is bounded by the weight norm of the weight change. So intuitively, this is saying, if you know how much you change the weights, then you know how much you change the outputs to first order. And mathematically, this is a Lipschitz bound. It's a Lipschitz guarantee with a constant of 1. And the second property is precisely the same thing, but for changing inputs. So it says that the linearized change, if I change the inputs, the linearized change in output of the module is bounded by the sensitivity attribute multiplied by how much I change the input. So this is precisely a Lipschitz guarantee, or a Lipschitz bound, where the module sensitivity is the Lipschitz constant. So the reason we don't need you might ask, why do we not have a sensitivity parameter for changing the weights? Well, the point is that we have the freedom to choose the weight norm. So we can define, if any constant for the weight sensitivity, we can absorb into the definition of the norm. So we don't need a Lipschitz constant. We can just set it to 1. So this is our definition of a module and a well-normed module. And I'm going to give you a couple examples. And the next thing is to define module composition and concatenation, but I'm not going to do that straight away. I'm going to give you some examples of modules first. But does anyone have a question at this point? Okay, so I'll just keep going and give you the example. So we're going to come back to this and complete the construction of the modular norm, but let's just go through some examples. So some atomic modules. So I'm going to give you a definition of a linear module and an embedding module, and then I'm going to give you the conditions under which they are well normed. So a linear module is just a matrix multiply, like take a vector, multiply it by a matrix. We say it has sensitivity 1. For now, we can give it mass 1. No, this is someone asked on the chat if this is some other notion of module from some other part of math, but it's not. Like it's something that we defined. It's more like a PyTorch module, but with some extra structure. So this is our definition of a linear module, and the norm we give it is the spectral norm with that factor of, that dimensional factor, like kind of absorbed into the definition. And the claim is that for this module, let's choose the input and output norm to be the RMS norm, like the Euclidean norm divided by square root dimension. Then if the inputs are less than 1 in the input norm, and the weights are less than 1 in the weight norm, then this module is well normed. So it's only well normed if its inputs and its weights satisfy constraints. How do we identify the sensitivity of a module? What you need to do is you need to take the forward function, differentiate it with respect to both the weights and the inputs, and then look at the definition of well-normedness and bound the size of those derivatives and look at what constant do I need to use to be able to prove that Lipschitz bounds. And what you'll see is that for a linear module, you'll see that with this choice of input and output norm, and under the constraints that I wrote, you'll see that it is well normed with a sensitivity of 1. So yeah, thanks for the question. So it's basically take the definition of well-normedness, take the definition of this linear module, and take those conditions, and you should be able to check that it's well-normed with that sensitivity constant. So how does an embedding module differ? Embedding module is different. It's basically, embedding is also, it's just the same forward function. It's like a matrix multiplication. So by the way, for embedding, I'm thinking of like the first layer of a transformer where we take a token index and then we pass it, you can think of that as a one-hot vector, the token index, and you do a matrix multiplication with a one-hot vector and it reads off like a row of the, maybe it's a column, it reads off, one of the embeddings from the embedding matrix. We also give it sensitivity 1. For now, let's just say it has mass 1. The big, do we have any? Let me answer that question in a second. So the big difference between embedding module and linear module is actually just the choice of norm. So for the embedding module, we give the norm as the max RMS norm over the columns. So you measure the RMS norm of each column is a different embedding vector. You compute the RMS norm of each embedding, and you take the max. And this is the norm. And this embedding module is well normed if we give the input norm to be the L1 norm and the output norm to be the RMS norm. So the idea is like, since the inputs to embedding matrices are one-hot vectors, you think about a one-hot vector as it's more like in spirit, it's a probability vector. Just where you put mass 1 on one coordinate and 0 on all the other coordinates. So the natural norm for thinking about probability vectors is arguably it's the L1 norm. So that's why we just give the input norm a different, and then we may as well give the output of the embedding matrix the RMS norm for want of a better alternative. And similarly, embedding is well normed under the same constraints, so long as the input norm is less than 1, and notice that for a one-hot vector that's true, and so long as the weight norm is less than 1. So long as no embedding vector has RMS norm greater than 1, then it's well normed under this. So this is like the thought process for building atomic modules. And the idea is that these sorts of calculations are, you can do them by hand. You could probably also, potentially in the next year, you could ask Claude or ChatGPT or so on to do them for you. But that's simple enough things that you can do them by hand without too much fuss. Someone asked the question, are there rank constraints on the matrices? And in the modular package or in our theoretical framework, we basically don't have any rank constraints. We don't need rank constraints. But yeah, I can talk about that a bit more. Okay, but this is the idea that atomic modules, you can write them by hand. And the same idea, for bond modules, they're even easier because they don't have weights. So you don't have to worry about the weight space aspect. You just have to worry about the input space aspect. So the bond modules are actually easier to write in most cases. And you can now imagine building a library of atomic and bond modules that you carefully understand their properties, and you're very careful. You put your numerical analysis hat on and think really hard about your library of atomic modules. Now we go back to the rules for composition and concatenation. So given two modules, we can put them in series. And we have to give rules for not just combining the forward function, but composing sensitivities. So we multiply the sensitivities, we add the masses, and then the norm is defined to be a max over the two subnorms with special multipliers. So what is the purpose of the multipliers, these P and Q? Well, first, notice that P involves the sensitivity of the second module. So the intuition for that is that if the second module is very, very sensitive, then you should be more careful about perturbing the weights of the first module. And that manifests as a stronger norm, a big, like the norm on the weights of the first module is just larger. And so that should be like a fairly intuitive thing, that if a second module is very sensitive, then you need to be careful about what you do to the first module. Interestingly, that sort of consideration, which is quite intuitive, is not been, as far as I know, it's never been formalized. And then the second thing is, notice that the P and Q involve mass ratios. So remember that mass is the thing that we sort of set by hand. So it's giving us the freedom to sort of tune the relative importance of the submodules in the norm. And there's a specific reason that we want that freedom. But I'm going to talk about that a bit later. For now, let's just keep going. So similarly, we define the rule for concatenating modules. And it's a bit easier. So it just means to get the concatenated forward function, you just take the forward functions of the submodules and write them as a tuple. To get the sensitivity, we just add. So there's no coupling in a concatenation. In a composition, there's a coupling, but there's no coupling in a concatenation. So okay, the masses, again, we just add. And then the norm is basically the same norm for composition, but it doesn't involve the sensitivity of the second module because, again, there's no coupling. But the mass, again, gives us the freedom to sort of tune the relative importance of each module in the concatenation. So this is now a complete definition of the modular norm, or you can think of it as a construction of this thing that we call the modular norm. But you may be, the natural question is like, why on earth did we come up with these definitions? And really, you can define anything that you want, but the question is, are these good definitions? And the reason that we claim that they are good definitions is because they enable us to recursively prove facts about compound modules. For instance, specifically, the combinations or the combinators, composition and concatenation, first of all, they're associative. That means, like, if you're going to, let's say, compose 5 modules, doesn't matter where you put the brackets. You can take the pairwise compositions in any order you like, and you'll always get the same underlying object. So that's a good sanity check. The second thing is that composition and concatenation preserve this well-normness property. So well-normness meant that we can have Lipschitz, we have Lipschitz bounds on our module. Well, as long as our library of atomic and bond modules are well-normed, then anything that we can build from our library using any sequence of composition and concatenation will stay well-normed. So in other words, the space, it's something like the space of well-normed modules is closed with respect to composition and concatenation. So that's great. And then, okay, the third thing is that feature learning is apportioned by mass. So you imagine you've built your GPT. What this construction gives you is it gives you precise knowledge of how much any layer or any subnetwork in the overall network is contributing to the change in output. So it gives you very precise knowledge of the internals of the network. The main use that we have for this is if we're training a big residual network or a big transformer, we just tune the total mass of all the blocks. So we give the input layer mass 1, the output layer mass 1, and then we have one hyperparameter, which is the total mass of all the blocks, and we tune that hyperparameter. So it's not like we tune one hyperparameter per layer. We just tune one mass hyperparameter for all the blocks, and it just sets the relative importance of the blocks versus the input and output layer. And we found that tuning that can actually improve the performance a lot. And it's not really clear what people are doing inside these companies, but kind of the impression that we have is that they may be tuning separate learning rates for different parts of the network and so on. So you can think about tuning mass a bit like that.
I'd ask a quick clarifying question about that.
Yeah, please.
Just to confirm, you said that we learn this, we pick this global mass value, and then the network learns how to partition this mass to individual modules with backpropagation. Is that the right understanding?
Not quite. It's more like, let me just tell you exactly how we do it. So when we build a GPT, we just give every atomic module an mass 1. So every linear layer gets mass 1, and every embedding layer gets mass 1, and every they're actually all the atomics that have mass, I think. Okay, so we just give the atomics mass 1. We build the network, and then if you think about it, after you've built the network, the mass of since module combination adds masses, the total mass of all the networks is equal to just the total number of linear layers plus the total number of embedding layers. So,
right.
But then what we do is we have we define a helper function called tar, and intuitively you think about like when you weigh things on a scale, there's like a tar button that resets the mass. So that's like how we came up with that name. But tar lets us reset the mass of any module and all its submodules to any value that we want. And we just tar the mass of all the blocks to like, let's say 5. So then after doing tarring, it's like the input layer has mass 1, output layer has mass 1, blocks have mass 5. And that means that each block has a mass of 5 divided by the number of blocks, if that makes sense. So tarring like recursively resets all the masses down the module tree. So that, does that make sense?
Yes, yeah, that makes sense. Thank you so much.
Okay. So it's not something that is, can the mass be set as a learnable parameter? Exactly, that it's, oh, no, not exactly. Yeah, no, we do not learn the mass. We regard it as a hyperparameter that we tune. Like, my inclination is to say, like, no, you should not learn the mass. Like, it should be a hyperparameter, but I can always be wrong about these things. So, yeah, it's something worth thinking about.
Now that you mentioned that it's a hyperparameter, I don't know if it's the right way to think about it, but does this transfer as you increase the width or the depth, or?
Yeah, exactly. So we ran some, admittedly, quite small experiments compared to what industry people are interested in, but we saw that it transfers across width. The optimal mass and the optimal learning rate transferred across width. What we did not see is, like, if you try like tuning the mass on a tiny data set, like if you, let's say you do the Shakespeare nano-GPT thing and you try to tune the mass there, you may want a different value of mass on a more complicated data set like open web text or something. And it's sort of, the intuition there is, maybe if you're training nano-GPT on Shakespeare, maybe you can actually just solve the problem with the input and output layer, and you actually don't need the hidden layers of your transformer. But maybe if you're trying to train a really complicated data set, you actually need, the hidden layers are actually much more important to the computation of the network. So you want to focus the learning on the hidden layers. So you would want to give them a larger mass. I think that roughly fits with what we've seen. So it's like, and another way to phrase this is that the mass can, well, it just sets how much learning happens in different parts of the network, and it gives you precise control over that. Yeah, and you could think about using it as, you could come up with like your Omni architecture, which has every kind of layer and every kind of operation, and then you could actually use the mass to interpolate between different model families or something. So there's other interesting things you could do that we've not really thought about so much or tested, but yeah, roughly, mass just gives you tight control over how much learning happens in different parts of your network. So I can't see the full chat. I just see the full. I need to figure out how to open the chat. Sorry, it's because I've got a. Someone asked the question, but I
can read it for you.
Thank you.
So the question says, so we actually also need to tune the mass besides the learning rate. The proposition is that it would be the same with scale.
Exactly. That's the proposition or the claim or the hope. Yeah. Okay. I think, so just to give you a heads up, so it's been an hour. I think there's 8 more slides if you want to keep track of how many more slides there are. And I think if there were no further questions, the rest of the talk would probably take another 10 minutes or 15 minutes. But I'm planning to just keep going with the same format where people can just ask questions and we'll just chat. But just to give you a heads up of where we are. So something that we explain in the paper is that this theory actually goes to second order. And actually, some of the considerations in the construction of this norm are actually intended to get the theory to work up to second order. So I just want to give a quick explanation of that. So intuitively, if you're training your neural network, you really want to know how smooth or how sharp the loss landscape is. And intuitively, that should somehow be important for setting the step size. Like if your loss landscape is somehow very sharp, then yeah, maybe you want to use a smaller step size and that type of thing. And what we do is we use the modular norm, the norm on the weight space, as enabling us to actually come up with a theoretical measure of sharpness or flatness using this norm as a length scale. And to contrast, people will often talk about the top eigenvalue of the Hessian or the top singular value of the Hessian as measuring sharpness or flatness. But what I want to point out is that that's really a Euclidean notion, because the spectral norm, or the top singular value or top eigenvalue of the Hessian, is really a Euclidean notion where it's the induced operator norm, where you put the input space and output space of the Hessian as being Euclidean space. And the big, what the thought pattern that we're trying to encourage is moving away from Euclidean notions to more general notions. So we define a more general notion of sharpness of any module, and we say it's alpha, beta, gamma sharp if the second derivatives obey the following bounds. So the things on the left-hand side are the bounds on the second derivative of the module contracted or multiplied with two deltas, and they're either both weight deltas, or for the second one is an input delta and one is a weight delta, and for the third one they're both input deltas, if this makes sense. So there's because a module has a weight space and an input space, there's actually kind of like three notions of second derivative that we might care about. And the thing on the right hand side is three positive numbers, alpha, beta, and gamma, and then the norms of the weight deltas or the input deltas. And actually the most general notion that you can have here is that the delta W, for instance, in the first relationship, there's two delta W's, like one has the tilde and one doesn't. That's a more general notion. So you should think about these as these coefficients, alpha, beta, and gamma. You think of them as generalized top eigenvalues. Like if you put Euclidean norm everywhere, these things would really just be standard spectral norms, or more like standard concepts. But because we're switching from Euclidean norm to general norms, we get like a generalized notion of what is a top eigenvalue of a matrix. And this is just our definition of module sharpness. But I'm just going to kind of give you the summary. The sharpness tuple, alpha, beta, gamma, what we show in the paper is that it obeys associative combination laws. So similar to like the combination laws we have for module composition and concatenation, there's additional rules for composing alpha, beta, gamma. So the sharpness of your submodules, you can automatically infer the sharpness of your composite or your concatenated module. And then we also show that we can extend the sharpness of modules to the smoothness of loss functions. So neural network loss functions are smooth in the modular norm. If you set up the architecture as we tell you to set it up, then you get non-dimensional smoothness Lipschitz constants. So like you can scale the depth of your network, and the network does not get sharper and sharper. You have like a smoothness of your residual network that's independent of depth. And the one assumption here is that the error measure itself has nice smoothness properties in the module output. So you think of something like square loss. Square loss is an incredibly nicely behaved function as a function of the output of your neural network, even though if you view it as a function of the weights of your neural network, it's quite complicated. Anyway, that's all I'm going to say here, and I'm happy to talk more about this. Okay, so I think this is the last slide before I just do the conclusion part. So I want to talk about our scaling thesis, and this is more intended as somewhat of a comparison with tensor programs. And the alternative title for this slide is like, why we normalize? Why do we have this normalized function in our code base? So our scaling thesis, or the way that we think about this, we call it a thesis because it's basically the idea that we have, but it's not, there's not like a theorem of this, or it's just an idea. But the idea is that if we build our neural network with Lipschitz constants that are both non-dimensional, so the constants don't change as you scale the network, And the Lipschitz constants are also tight, meaning that as you scale the network, the bounds don't get slacker and slacker. They stay at the same tightness with scale. Then your learning rate will transfer. So to spell this out a little more, if for a generic module we can achieve the following conditions. So one is the Lipschitz constants are independent of width and depth. And the second is that the bounds stay tight across scale. Then this implies that controlling the modular norm of our weight updates gives us control over how much the outputs change at any scale. So this is why we normalize the updates to control that weight space norm in order to give us control over output space norm. And notice that because the modular norm is defined recursively, doing this actually gives us that control, not just for the overall network, but also for any submodule. And to put this more formally, we want to have this Lipschitz guarantee that the change in output is bounded by the change in weights. Think of this as the first well-normness condition. And we want this to hold tightly. And intuitively, it's somehow tight. An inequality of this form will be tight when somehow the change in weights kind of aligns with the input to that module. To get the intuition about that, just think about a linear module. And you can actually prove that this form of alignment occurs if you go like batch size 1, and you can also do things like take the width to infinity. You can just basically you don't even need the infinite width limit. Just look at batch size 1 and you can see that this happens. And this is the tensor program's approach. But some of the kinds of things we're trying to point out to people are that modern training actually severely violates that limit. Like if you do big LLM training, it's actually more like a batch size. It's more like an infinite batch size limit with a finite width in a sense, because you often have a batch size of like over 1 million, and you have a width of a few thousand. So it's actually outside the tensor program's regime, but it's still described by the bounds that we have. The bounds we have are, they don't care about batch size. So I want to give a sales pitch for this idea of metrized deep learning, just to finish off. And again, for me, like something really exciting at the moment is this Shampoo optimizer, which is described in the Shampoo paper, and it won this, a variant of it won this competition recently. And what I want to argue is that the core primitive in Shampoo is this weight update. So G is the gradient matrix, and you do this funny thing with matrix powers, and you do GG transpose and so on. It's a bit difficult to interpret. But what I pointed out on my Twitter thread is that this funny Shampoo update actually solves a simple optimization problem, which is referred to as steepest descent under the spectral norm. And so I want to argue that actually Shampoo is like what I would refer to as like a metrized deep learning algorithm in disguise. Yeah, this is a link. I can share the slides after, and I'll put them on my website. But I argued this here, and there's a very simple way to implement this in modular, just by overriding the normalize function of a linear layer. So just to quickly point out that funny Shampoo thing, you can think of it as just taking the 0th power of your gradient matrix, by which I just mean take the SVD and set all the singular values to 1. So I coded this just with like a proof of concept implementation. And we just define a Shampoo linear layer, or a Shampoo linear module, by overriding our linear module. So we call the super function of the super module of the linear module, and then we just override normalize. We get the gradient of the weight matrix. We take the SVD, and then we just throw away the singular values. So in other words, we set them to 1. But we define this to be the normalized function for our linear layer. And I ran some quick experiments. Admittedly, this is like a super toy. This is like an experiment that runs in less than 15 seconds. So it's that kind of toy. But we compare vanilla gradient descent, our naive form of modular normalization, just dividing by spectral norm, and then this kind of quasi-Shampoo algorithm. It actually saw in this experiment that it converges much better per iteration. Using this new normalized function. So this is something I'm quite excited about and thinking about at the moment. And it's trying to take Shampoo and fit it into our framework, which I think is quite natural. If you get the slides for the talk, you can click the Colab link and it will take you to the Colab for this. So again, I think that this metrized perspective could also be useful for thinking of. Thanks, Felipe, or Philippe, thank you. Again, I think it can be useful for low precision training. I think it could potentially be useful for, taking another pass or having another go at adversarial robustness. And we cast both of these questions as fundamentally questions of module sensitivity. Another area where I think metrization could be really helpful is confidence intervals. I'm just like throwing this out there with the hope that someone would pick up this thread again, because it's something I haven't looked at for a while. But the idea is that when you want to know something about the confidence of your neural network, intuitively, there's a quantity called margin, which is basically the size of the predictions, and this should be important. But I want to argue that margin alone is meaningless, because you can scale the weights and you can inflate the margin, or you could scale the inputs and you can inflate the margin. So somehow you need to divide by the size of those quantities to have like a meaningful notion. So you need to define some kind of normalized margin. And I wrote some papers on this topic, and Ben and Neishaber has a great paper on this topic, and there's a few different papers on this topic. I think that this is an area where rethinking these topics with metrization in mind can be very productive. So just to give you some related literature, for me, this metrization idea starts with this Fromage paper that I did on my NVIDIA internship. MuP came like a year later. I did a project called AGD. There's a really great paper called Autobound, or a really great from Matthew Streeter and his collaborator. I highly recommend reading that paper. It's like inspired this project a lot. And then we ended up with this modular project, which I'm really excited about. And you can install it by pip. And I wrote some docs and trying to create some other resources for people to learn about the project. And yeah, thank you for listening, and I'm happy to answer any more questions if anyone has them.
I had a couple of questions, if that's all right.
Yeah, go for it. Thank you.
There's a couple of them, so if anyone else wants to ask questions after in between, feel free to totally jump in. First, thanks so much for this talk. I thought your paper and your library are exceptionally well written, and I just thought it was a really cool, new, promising research direction. I guess my first question is, where do you see this stuff going? In some ways, I think people would be really excited to see some very large-scale experiments. You mentioned a bunch of other possible future directions. I guess, how do you see this type of thing playing out if people were to use this like spectral normalization idea a lot more?
Yeah, great question. I'm gonna give you my craziest, most out there answer, because maybe it's the most fun. But it's like, so Andrei Karpathy tweeted something about we could build a new computer where like LLMs are the operating system, and like what does that even look like, and what does that mean? So for me, like the interesting question is like, what is the operating system for this computer? Like, imagine we build like a fully learning machine that just, you interact with it, it learns from you, you learn from it, it helps you, and so on. Like, what is the OS for this machine? And okay, maybe there's some like computer science OS, like you need CUDA, you need to be able to do that stuff. But I'm like, what's like the kernel for learning, and like what does that look like? And okay, maybe it's like PyTorch, or maybe it's like JAX potentially, but they are somehow they're all built on some philosophy, and I think as we understand more and more about deep learning, we can just build a better and better philosophy. And I see that like that's kind of how I want to think about this stuff, is just like what's like the low level code for learning, and like what's the wackiest thing you could do, like build a new computer chip that's like built on this instruction set. Like what's the instruction set? Like if you could just have $1 billion and build your own like chip factory, like, and you get to build it from scratch, what do you do? And I think it's the idea of like wedding the technical knowledge of chips and electronics and hardware and so on, and then the technical knowledge of like learning and neurons and putting those things together. And that's like the big vision. But like like what's the small vision that's just like writing Twitter threads and trying to get people excited? I don't know. And then where do I like I didn't know if you remember the slide about the, let me see if I can bring it up, like the module design slide where I was showing you like designing modules, and like it's like I kind of, what I'm hopeful for is it's like the clever version of deep learning where you're like, let me give this module this norm on the input space, this norm on the output space, like what happened. It's like allowing you to reason locally and then automatically get global properties. But we've not thought, that hard about all the local properties. Like we've thought somewhat about it, but we haven't experimented that much. And I feel like to cast the problem is like module design, like atomic module design, and then what emerges from that. And one example is like, hey, you can change the normalize function from the spectral normalization to shampoo normalization. That's something you can do. Like something we write in the paper is that you can move from RMS norms to infinity norms. Like that's something that you can, there's like a big design space, and we've not really explored a lot of it. So that's what I want to try to get people excited about it, or get people to think about it. And but yeah, I don't know.
Got it. Thank you for that inspiring answer. Yeah, I think it opens up definitely a lot of very interesting design choices. I have another question I'm happy to ask, but I want to give an opportunity in case anyone else also wants to ask a question.
Yeah, let's just give 5 seconds. Does it because it's better to have a diverse. Yes. Oh yeah, please, Gabriel.
Okay. A little question. Does the normalization introduce how much overhead does the normalization introduces?
Yes. So great question. So our current implementation, we do spectral normalization via power iteration. And we're not like CUDA people, so it's not super optimized. Like I learned about torch.compile at the end of this project and so on. And it's like I think on our simple benchmark, it was like a 20% overhead. But the thing that gives me faith, and the point I want to raise, is that Shampoo is a more intense form of normalization than what we're doing, and it won the speed challenge for the AlgoPerf thing. So like, I'm pretty confident that like the overhead is going to be manageable, but we personally have not validated that. But I think that by some hybridization of what we're doing with Shampoo, and like, yeah, I'm not worried about the overhead, but I was worried about the overhead.
Yeah, nice, thank you.
Yeah, again, if anyone has another question, just jump in. But otherwise, Gilad, yeah, feel free to jump in again.
Okay, I'll ask the question. I haven't had a chance to look so much into the mathematical details yet, though I'm definitely hoping to. But I was wondering if you can talk about how this might compare with U mu p. I saw that came out a little bit while ago. What's the connection?
Great question. So I've been talking with Charlie Blake, who was great, and yeah, highly recommend reading. So it's called Unit Scaled Maximal Update Parameterization, and it focuses on a different question. It's slightly orthogonal to what we're doing. So it's more about their concern is they really want to get low precision training, and they want to center, my understanding is that they want to ensure that all of the quantities in the network are centered around one, so that things fall into like the nice dynamic range of like a nice low precision number format. And the observation they have, I may be missing details and I need to go through it more carefully, but there's various symmetries in maximal update parameterization. Also in what we're doing, there are various symmetries where you can move factors around and nothing changes. And you can use that, you can be clever about that to like move factors around to like get numerics to be better. And my sense is that that's what UMP is doing. I'm talking with Charlie because I'm hoping to like integrate those ideas into what we're doing. Just to give you an example on this slide, like you see here, the spectral norm has this dimensional factor. You can move that dimensional factor to the forward function and then not have it appear in the norm. So there's a freedom there. And you can start to think about being clever about that freedom. And there's other things you can do as well, but there's more freedom. That's something I want to highlight is that MuP paper, if you read it, it sort of gives you an impression that there's one kind of unique parameterization. But it's a slightly misleading because there's actually a ton of symmetries that you can exploit to like move factors around. So I would say I would not describe it as there's a unique parameterization. I would just say like you should make sure that you're matching norms or something like that. But there's actually a lot of freedom in how you parameterize, and I think you can exploit that to get better numerical properties. But we haven't explored that yet.
Thank you so much. I have one more question, but again, I'll let someone else ask in case they have first. Okay, I think I'll just ask it then. I've been thinking a little bit about different types of structured matrices for our weight matrices. And I was wondering if you think this may be applicable to that. In particular, there's a previous paper of a collaborator of mine that was submitted to NeurIP, so it's not available publicly. But a key part of it was they showed to get these structured matrices to work, using plain vanilla MuP was actually very important to them. And I don't know if you've looked at this literature at all, things like monarch matrices or butterfly matrices. If you are familiar with this at all, I was wondering if you think this would be applicable. And additionally, if some of these module definitions would need to be implemented, if that's complicated or not, just what are your general thoughts?
Yeah, great question. So to answer it in a few different ways, but first of all, our hope is that you should be able to take our package, take our linear module, and compose them in any way that you want to build structured matrices, LoRa, Monarch. I'm not super familiar on like butterfly and all of these things, but you should not need to think. Like this is the goal for modular, is that all you do is you think, I'm going to build a linear module. I'm going to put all my effort into carefully building a linear module. Now, if I want to build like a LoRa or a Monarch or something, I just compose my linear modules, and they should automatically get, have good width scaling and good. So I actually, I at one point was like, oh, I got really into structured matrices. Like I thought I was thinking of it for myself, and I was like, oh, I've got to write a paper on like some kind of structured sparsity, because it's super. Once you think about this perspective, it's quite natural to start thinking, how can I apply it in different settings? And then I like thought through, and I think it turns out like what I thought about was basically Monarch, and it turns out that they'd already published it and so on. Anyway, it's like But the idea that we're trying to put across is that this is somehow a general framework which can handle lots of different of these things. The second thing I want to point out is that Shikai, I'm forgetting his last name, but he's a student with like Andrew Gordon Wilson, and he also has a paper recently about like structure. They call it tensor train or something like block tensor train, and
that's one of the papers I was thinking of building off of.
Right. Yeah, exactly. So I think it's great. Yeah. And my hope is that the kind of tools we're building can be used to make it easier to build that kind of thing. But obviously it requires some kind of buy-in for people to want to use our tool, or like they need, and you can just like look up the spectral conditions and just implement things manually, and maybe that's the better approach. I don't know. But yeah, I'm super excited about those directions. Like I'm reading those papers, and yeah, I think it's great.
Okay, thank you so much. Yeah, those are all my questions. But I think this whole stuff is really cool. And I also just wanted to give another shout out. I think your documentation is amazing for Modula. And I think it makes it very helpful for people to get started and see the advantages of
it. Thank you. I just went through like, we wrote the paper, there's like an intense period of work up to and then I was like, I don't know what to do with myself now we finished writing the paper. So I'm just going to keep going. And then I like burnt out and then like went on vacation or something. But yeah, I'm glad that, thanks for the feedback. I appreciate it.
Yeah, I think they're excellent.
This is what I'm noticing as just like random digression, but I've started putting a lot of effort not only into like doing research, but also in trying to communicate it. And it's been really valuable for me because I think like if I want to work with new collaborators, it's easier for them to get up to speed. I got like more positive feedback from people in the community for doing it. So yeah, I feel like it's been all around pretty good. Like, and anyway, that's yeah, I'm planning to try to continue doing that.
Yeah, I very much commend your efforts for that, and I definitely see a similar pattern. Because if you have like an online presence, people will be like, "Oh, this is really cool. I extended this. I extended that."
If you what? Sorry, if you.
I was just saying it's very cool if when you do things online and spend a lot of time communicating it and writing good open source software packages, because people can just add to it, which is pretty nice.
Yeah. And yeah, exactly. It is nice. And like I got in touch with this person, Jack Gallagher, and I honestly learned a lot from him. And he just implemented things in Jax, and like that's pretty cool. And like now I'm trying to learn Jax and trying to think a bit more broadly as well. And yeah, it's been nice.
Yeah, well, thank you so much. I think I'm gonna head out personally, but excited to keep taking a look at this and exploring myself.
So thank you. Yeah, great to chat with you. Thanks for the questions. I think, yeah. By the way, no one's under any pressure to stay. I'll probably just stay because it's nice to chat. But I think Ahmad asked something in the chat about how does it work for fine tuning. So I think that's fine tuning is a big advantage of our approach. Fine tuning is a big advantage of our approach over tensor programs because, as far as I can tell, all the tensor programs arguments rely on, Gaussian initialization, and like it says nothing about how things work in a fine tuning setting. But all the analysis that we have is valid at any stage in training on any model. The one caveat is that we these well-normness conditions on this slide, at the moment we're only enforcing them at initialization, and so like if you just take an off-the-shelf model and you want to fine-tune it, those conditions may not hold. So we're thinking about how to deal with that, and we're thinking about trying to build a new version of the package where the guarantees hold at any stage of training. And then this would give you very good knowledge of the model that you're going to fine tune as well. But we haven't got that yet. But yeah, that's a selling point. Basically, a selling point for the framework and the analytical framework that we have is that it should be applicable to any neural network, any stage of training. Doesn't rely on random matrix theory. You don't rely on special properties of initialization and so on. It's just the type of math that we're doing is just bounding derivatives. How big is a derivative? And how big are quantities in the network, and just bounding those things. No probability, no random matrix theory. Very generally applicable.
You also talk a little bit about interpretability as well. So can you talk more about how it improves the interpretability of model?
So is the question just how does this relate to interpretability?
Yeah, and like how can it improve the interpretability, like the interpretability for large language models?
So kind of improve the interpretability for large language models?
Yeah.
Yeah, interesting. The aspect of interpretability that it gives you is it gives you pretty good understanding of what's happening internally inside the network. And it's the results like, this proposition 3, feature learning apportioned by mass, like you have good knowledge of how much any submodule is contributing to the overall whole. It's not interpretability in there's a traditional sense of like, giving me a verbal explanation of how the model made its decision or something like that. I didn't really know necessarily how to think about that yet, but it does give you more like fine-grained understanding of how much any submodule is contributing, how much change is happening because of changes to submodules. It's like you think of your overall neural network and you decompose it into a tree. We think of the module tree, where the leaves of the tree are the atomic modules, and then it's a binary tree where you take a composition and you get a subnode, or you take a concatenation and you get a subnode, and then you build your network up in this tree fashion. And what this style of argument does is it allows you to apply recursive reasoning to understand the influence of any subtree. So that to me, this is a really big thing for kind of some kind of theoretical interpretability, or having good control over internals, is like this control over any subtree and this recursive style of math, basically. So that's how I think about that. So yeah, maybe if there's another question, I could take it. I'll just quickly say that if anyone wants to chat more, my email address is on my webpage. And my webpage is my name, but with a dot before the IN. So feel free to reach out. I'm traveling at the moment, so I may be a little slow to respond, but yeah, if anyone wants to reach out, that would be great. Oh yeah, Alma just posted my website in the chat. I'll post my slides on my website some point soon. Yeah, again, like really grateful for being here to talk. Yeah, it seems like this seminar series is great, and yeah, I'm grateful to be involved.